conference because I mean it's the same talk, only the first slide has changed. Okay, so let me start. Okay, so one of the things, so it's kind of a folklore that that we know that in AdS-CFT, the extra spatial dimension which you have, that can be identified with the renormalization group scale of the field theory. Now, the thing that I mean that's still kind of a folklore type of thing, in the sense that it's not clear that if you go beyond a very specific class of geometries which are known as tokenal geometries, that how this connection between the extra spatial dimension and the field theory AdS-CFT works out. So in this talk, I will actually try to work out some of the old stuffs. For example, the proof of the holographic c-theorem in the bulk in the standard tokenal type of geometries in a slightly different way. And then what I will do is that I will apply that particular way of proving the holographic c-theorem to more general type of asymptotically AdS geometries, for example, black brain geometry, or okay. So that's the one concrete example, which is not of the standard holographic RG type of geometry that we usually talk about. So in this talk, the probe that will be the object in the bulk that we will use to prove the holographic c-theorem is actually the icon of a boundary point in the boundary point in AdS. For example, this P is a point on the AdS boundary, and this is the future light cone of this point P, and this is the past light cone. And for simplicity, what I have done here, that I have considered the pure AdS metric in the pointer slicing, which is given by a metric of the form that ds square equals L square over z square times this metric, which is eta mu nu dx nu. So this eta mu nu is the standard Minkowski metric, and this z is this orthogonal direction to the AdS boundary, and z is here a space-like coordinate, and this L that is the size of the AdS space. Okay. So now, so one of the things which actually motivated the connection between this extra bulk dimension z and the AdS-CFT is that in the bulk there is a scaling symmetry which acts like if there is a point in the bulk with coordinates x, mu, and z, then you can rescale the coordinates, which is say you rescale it to something like lambda x mu and lambda z. And as you can see that if you rescale x and z by the same quantity, then this metric does not change. And the thing is that so there is a corresponding killing vector field, which is given by this vector field D, which has the form this x mu dx mu, plus z d del z. Now, one thing which you can do is that, say, let's compute the norm of this metric, this norm of this killing field which we have here, which has this particular form, and then we can see that this killing vector field is null on the hypersurface sigma, which is given by this equation, which is eta mu x nu plus z square equal to 0. Now, this sigma is the bulk light cone of the boundary point, x mu equal to z equal to 0, and so this sigma is this. So I am just looking at the future light cone of this point P, and let's assume that this P, that this point P has coordinates x mu equal to z equal to 0. Now, it turns.
So when you say symmetry, you really mean after you redefine parallel, you get the symmetry?
No, because the thing is that there
one by z
are
square
two
is
powers of x and z here and two powers of z here. So yeah. So if you rescale by the same amount, then they will cancel. Right. So this sigma is the bulk light cone of the boundary point P, which I call x mu equal to z equal to 0, and it's a killing horizon which is generated by the killing vector field D. Now, so the okay, so we can see just from here that if I look at the null geodesic generators of this future light cone, then they have zero expansion and shear in pure radius. Now, let me point out that this vector field D, which you have here, if you just look at the restriction of this vector field to the boundary of the AdS, which is located at z equal to 0, what you get is just this standard scale transformation of the field theory, which is x mu del x mu. So this D actually generates the scale transformations of the field theory.
So are you saying that whenever the D becomes null,
yeah, so
there is this result that there is zero expansion, zero scale?
No. The thing is that the thing is that D is a killing vector.
Yes.
So that means this null hypersurface, that's a killing horizon. So that actually gives you that theta equal to 0 and sigma AB equal to 0. The rotations are automatically 0 because it's a null hypersurface. So it's just like a horizon of a stationary black hole. So it's a killing horizon, and nothing really changes there. Okay. So now.
You mean by using the Shamik equation and
yeah, just the fact that okay, so yeah, so here the thing is that these non-geodesic generators of sigma, they are just D, this vector field D.
Yes.
Now, if you so what is the expansion? I take a space-like slice of the null hypersurface and I transport it along the vector field D, which is a null geodesic generator in this case. Now, since it's a killing vector, the transporting is an isometric. So
theta equals 0, I get that.
Yeah.
So why is sigma?
Because of the actually sigma AB is also 0 in all these domain 1 type of geometries. Also because of the Lorentz invariance of the cross sections and these things actually.
More generally, it's 0 for any killing horizon.
Yeah, so it's just like a black hole horizon actually. So omega is 0.
Yes.
And then you just decompose it, this something like LSIB, we decompose it into this, and then we use the Killing equation. So it's okay. The more familiar situation is just the horizon of a stationary lag.
There is some amount of
no matrix falling in things, because if you look at right to the equation, if the shear is not zero, then even if the expansion is zero at some instant, then it can't be zero because there is a sigma square. So everything, I mean, it's just a property of, like all the spatial cross sections are same. Yeah. Right. So now, okay. So now, one thing is that, okay, as I said, that is D can be so this D restricted to the Z equal to 0. That's just a standard scale transformation of the boundary field theory. And the thing is that, so now if we look at RG flow, so RG flow is essentially can be thought of as a breaking of this scaling field theory scaling symmetry D. So if I consider RG flow in the boundary field theory, then that so that means I'm considering field theories which are not invariant under scale transformations, and that means that leads to a breaking of this scaling symmetry T. And in that case, what one can see is that this bulk light cone, that's no longer a Killing horizon. Now to see that explicitly, what you can do is that we can take domain-wall geometry, for example. So of this form, that now we have the same type of metric, except that this we have a new function which is f of z, which is not there in the pure AdS metric. So right. So this particular geometry is for the three-dimensional, so AdS3 case. Now, if you apply the null energy condition, what one gets is that this f prime of z, which is just dz of fz, that quantity is actually greater than equal to 0. Okay, now. So this fz satisfies the constraint that if there is an interacting, if there is a non-trivial interacting CFT in the infrared, then as z becomes large, this fz goes to L square over L infrared square, where L infrared is the size of the locally AdS region at large z. So now let's look at, okay, now let's write down the equation of the Lyotard cone, or the bulk Lyotard cone of this particular point, which is x mu equal to z equal to 0. So it's the same.
I forgot the definition of fz. Could you go back?
Yeah, so fz is just this.
Yeah, okay, fine.
Okay. So now I consider the same. Okay, it looks the same geometry, but the thing is that the light cone will now change because the metric has changed. But I keep the same point P with coordinate x mu equal to z equal to 0. Okay, so now the equation of the light cone sigma bar, that becomes this, which is minus t square plus x square plus z bar square equal to 0, where we have defined this coordinate z bar as this, as some integral of dz prime by square root of fz prime. Okay, so now this sigma bar is essentially the deformation of this sigma. Well, okay. Now the null generator of this sigma bar can be taken to be of this form, which is d bar, which is just this t ddt plus x del x. But now instead of z, I put this z bar and then del z bar. Now this d bar is not a Killing vector field except asymptotically as z goes to 0 and z goes to infinity, where scaling is recovered. Now it is easy to see from the domain wall metric. So I have written the domain wall metric in this particular form, z bar square, where z bar I have defined this coordinate since it is just dz by square root of h. So that is dz bar. Okay.
Question, I think.
Shamik.
Yes.
Yeah. So how does f of z behave as z goes to 0? Does it go to 1?
Yeah. Right. Yeah. So as z goes to 0, this fz is going to just 1 because this metric reduces to this metric. Okay. So this
and z bar starts is same as z, near z equal to 0. There's no coefficient there.
Near z equal to 0, z bar and z are the same.
Yeah, so that can be seen from here actually. If you take z to 0, then z bar just becomes z because this fz is actually going to 1. So z bar is actually z near z equal to 0.
And f of z equals infinity also goes to a constant, right?
Yeah, so that is this L square over L infrared square. So this L, so this L is the size of the ultraviolet AdS that we have. Okay.
And you see that by just rescaling the x's and absorbing the overall into the n.
Yeah. I mean, you can just do here. So this z actually becomes z bar over z. I mean, just to scaling. Right. So so just from this now this d bar. So now I am thinking of this z bar as my new coordinate instead of z. So this z now should be thought of as a function of z bar. So which you can get by solving this. So you can solve for z in terms of z bar from this equation 9. Okay. So now you can see that these generators which are here, this d bar, they are becoming killing as z goes to 0 and z goes to infinity, and that's intuitively clear because the point is that the field theory is going from the ultraviolet conformal field theory and then it flows to the infrared conformal field theory at large values of z. And at the fixed point, the scaling symmetry is recovered. So this d bar becomes, this is just a statement. The mathematical way of saying is that this d bar is becoming killing vector near z equal to 0 and z equal to infinity.
Some other choice of d bar.
No, not. What do you mean with some other choice of d bar? So this d bar as a vector field.
At infinity, I mean, f of c picks up some constant.
Yeah, but that cancels, like it again becomes like, you can just think of it like that also. Like that will cancel with this actually, this z bar. I mean, z bar is just a constant multiple of z as z becomes large. That can be easily actually seen from here as it becoming large. You can actually just solve it from here, right? For mostly.
I mean, I can absorb those scales in t and x.
Yes,
that's what you mean.
Right. Actually, the best way to think about it is that just think of it as this in this coordinate. So this z becomes just a constant.
Okay,
so this metric just becomes z bar square. Scale infrared square by z bar square, and that has this symmetry.
After rescaling of dx.
Yeah, so here actually you have to rescale things
dx
properly. Okay, and yeah, actually one can explicitly check these things and yeah. So for example, okay, yeah, I have just checked everything here, but I'll just come to that. So I'll just let me do the picture. Okay, so the picture we have is something like this. So when we have we have the ultraviolet ADS, and then we have the RG flow. So if we look at the future light cone, so that becomes giving horizon near the ultraviolet ADS and the infrared ADS, and there is an RG flow, and all through this RG flow, this sigma bar is not a killing horizon because the scaling symmetry is broken. Now, okay, so this is similar to the situation where we look at a black hole and say if we throw some matter into the black hole, so the black hole actually starts in a stationary state, and then some matter falls through the black hole horizon, where and when it is, and at that time it's not a killing or a stationary horizon, but asymptotically it again becomes stationary. And the thing is that it's known that in those cases, the entropy, the Bekenstein-Hawking entropy of the black hole increases. So that's the second. Okay, so we can actually, so let's see that if we apply the same thing here, what we get. Okay, so these are actually considered independently of black holes by these people, and they showed that if you look at, okay, so since I'm looking at the future light cone, so that's the past causal horizon of this boundary point T. Okay, so for past horizons, this expansion is actually less than equal to 0, and that's the statement of the second law, and that roughly tells that as you move forward in time, the Bekenstein-Hawking entropy decreases. Now, this uses Roy-Choudhury equation, and there is some fact that the light cone is the boundary of the chronological past or the future of a point on the conformal boundary of AdS. Now, the second condition acts as a cosmic censorship in this case. But okay, so there are some here, but okay, so we will not take that very. Yeah, so that's the motivational part. But we will actually check this thing explicitly in all the
future is confusing. Sorry.
So the future horizon, that's the boundary of the past, and the past horizon is the boundary of the future.
So if you've got an event, if you've got a horizon such that towards the future the geodesic is never positive.
Correct.
Then
that's the future.
Yes. Then the expansion is always positive.
Yeah. But if you now look at this horizon, like this one, so theta is 0 here.
I don't understand your diagram. That's black hole?
Yeah,
I agree. That's black. If theta is greater than 0 here, then less than equal to 0 then. Yeah.
So that's
in your thing, towards the future, it should be greater than equal to 0.
No, it is less than.
This I didn't understand. Explain why.
Yeah, so this is like this, right? So this is like the past. This is the future. Sorry, this is what? This is the boundary of the future. So this is the past horizon of the black hole. So one way to understand is that theta is 0 if you are here. Okay.
Actually, I thought the rule was that in an event horizon, theta is always positive in the direction towards which there are no cosmics.
Yeah. So you agree that here the expansion is 0.
Wait, not black hole. This is black hole or your AdS situation?
Black boundary. Yeah, black hole.
Okay.
Some black hole. Okay. Or here you can also between this. Okay, so this is the time direction.
Right.
So this is the horizon. So this is the horizon that I'm considering. I could also consider this.
Yes.
So it does not really matter. Now the point is that if I move in positive t, so this is the future horizon. So theta is always greater than.
Sorry, just one second. Somebody's microphone needs to be muted. Some microphone is not muted.
Check with them.
Yeah, so there is no caustic formation.
Wait, but there's no. Here you have caustic formation towards the future, right?
Where?
At that boundary point.
No.
Why not? All the generators.
Yeah, but that's not a caustic, like because of the infinite volume.
I see. So yes.
So I will just explicitly show that there is no caustic formation or nothing. I mean, it's just easy to see actually.
Okay,
and that's just because of the infinite volume.
Nonetheless,
you will see that the area is just a constant number there.
I see. But sorry, your definition was this is the light code of a point, right?
Right. So the thing,
So don't they all meet at that point?
Yeah, but the thing is that by caustic formation, you mean when A is going to 0. But here, this A is not going to 0 because of the 1/z square blowing up.
I see. And does it caustic in the past?
It may or may not, but I showed in this case that it does not.
It does not. But then you have a contradiction, right?
No. Yeah. See, just
okay,
clear with me. And,
yeah.
So these can be actually explicitly checked, like
okay. But just to say, if it doesn't caustic in either the past or the future, then we prove both.
Yeah,
theta greater than 0 and
no. Wait. I think what is happening here is following. If you look at the Poincaré patch,
yeah.
Okay, so if you go like this, or say if you wish, you could also go like this. Okay, now it becomes stationary here.
Okay.
Just like a stationary, also stationary here.
Yes.
And the thing is that in between, this theta is actually greater than 0. I mean, that's just a statement that this P bar. Okay, so I just check everything explicitly that.
Let me just say my confusion again. My confusion was that if there is no caustic in between, you prove monotonicity in one way.
Yeah,
I thought that meant that there had to be a caustic the other way.
No, but why do you expect that? I mean, there has to be a caustic.
Because otherwise you could put the theta dot is greater than 0.
Caustic. But the thing is that, I mean, why is it necessarily forming a...
Because I thought that one way you prove that theta dot must be greater than equal to 0.
Yeah.
Then if you do it the other way...
Okay, I mean, theta dot is less than...
theta double dot, sorry.
Yeah. No, I mean, theta...
theta double dot is less than equal to 0. Yes.
Theta or...
Yeah. Now you went from stationary to stationary.
Yeah.
So suppose you got the theta double... But let's just work with theta double dot. One way to prove that theta double dot is greater than equal to 0.
Theta double dot, like the Rajati equation, just gives you theta dot.
Theta dot is less than equal to 0.
Less than equal to 0.
Then if I run the proofs the other way, I would prove theta dot is greater than equal to 0, right? Because all that the proof assumes is that there's no singularity of the generator sum.
Which is what happens for the white horizon.
Yeah, so in this case, okay, let's just go to this.
Yeah.
Yeah, so that's why I said that let's not take this thing very... Like, the thing is that I mean, this is a much more complicated thing to prove than the black hole horizon. Okay, so let's just do this templation explicitly, and then one can see that what is the thing that one is actually getting in this case. So let's just take what is okay. So now we look at the cross sections of this light cone, and what you get. Okay, so let's take the null generators. So this sigma bar is the deformed light cone, and let's take the null generators of this sigma bar to be the integral curves of this d bar, which is parameterized by lambda. So I have this vector field d bar, and this is the null generators. They can be parameterized as integral curves of this vector field d bar. So that means it solves this equation, and lambda is not necessarily an affine parameter in this case. Okay. Okay. So now let's just. So I'm looking at the AdS-3. So now the if I look at a space-like cross section of the future light cone, so that's a curve. And if I look at the induced metric on the slices, so that is just the equation of sigma bar is this, and I now look at the induced metric on this null hypersurface, and that induced metric has this form, this L square. This one, this z bar is that quantity as a function of lambda. We know what it is, and we have we know z as a function of lambda by solving this equation. This equation, and that gives me this quantity. Okay, so now, so this is the induced metric or the length of this spatial cross section, and this eta is a co-moving coordinate which is parameterizing a space-like slice of this light cone. In this case, the slice is just one dimensional. Now, from here we can define density of the Bekenstein. See this eta. This eta is independent of lambda because this is just a co-moving coordinate. And
actually, I haven't understood what this eta is.
Oh, this eta is this coordinate actually. This cross section, the curve. This is eta.
And you're taking the.
So
you're taking a little. I see.
Yeah. So just little area.
And you're using isometric. There should be many directions.
No. This is just.
Oh, because we AdS-3. I see.
So I can't do
What is AdS-3?
many directional
Questioning.
Yeah.
Question? I see
wanted to see the board. We just wanted to see the board.
You want to see the board? Yes. That was. Yeah. Now, is that better?
Okay.
Can you see the board? I see. Yes. Oh, I see. Whoever.
Yes. Shamik, can you just repeat what you just said?
Oh, so Siraj asked that why is there only one eta? I mean, it's only one eta because it's a three-dimensional space, so it's a four-dimension too, so there is only one eta. So then, okay, in the next slide we'll have more than one. Okay, yeah. So we have this. So now we can define this Bekenstein-Hawking entropy density, which I am just defining in this way as this co-moving constant of the ds Bekenstein-Hawking by d eta as this quantity, this 1/4 g Newton L z bar over z, and statement of the second law as applied to this or this, and whatever you can do it either way. And if dd lambda of this quantity is actually less than equal to 0. Okay.
Wait. I thought along the dd lambda vector, this z bar divided by z was constant.
No. This z bar divided, no. Why it is constant? Because the thing is that this is the induced.
Sorry.
This is the induced length.
Yeah.
And then it is changing if you take different space-like slides.
So I thought I heard this.
Okay, but you don't have to believe this, but it's too okay. I mean, in this geometry, it's too easy to compute this. Okay, I haven't shown the computation, but it is in our paper. You can explicitly check. And the thing is that you can check that both. If you take, okay, so let me just show you one thing. that this as lambda goes to minus, so this equation, if you just trivially do, so as lambda goes to minus infinity, this z bar actually goes to 0. So that implies that z is also going to 0. And as lambda goes to plus infinity, this z bar also goes to infinity, which is also then going to infinity. Okay, so what one can show, I mean it is just one line exercise. If you compute this quantity, this z bar over z explicitly, then this is actually less than equal to 0. And the thing is that if you compute this dt lambda of z bar over z, so not only it is less than equal to 0, this as lambda goes to minus infinity, this quantity is actually 0. And also this is 0 as lambda equals plus infinity.
Yeah, that's going from stationary to stationary.
Yeah, so that's just the, so this is just the statement.
Now, but the inequality must use the positive energy condition somewhere.
Yeah, because the things that when you prove this, what you use is this condition that this f prime of z is actually greater than equal to 0. So that follows from the Zamolodchikov condition.
And that is like the standard proofs of the c-theorem go the same way?
No.
Okay.
Because the standard, I think the standard proof, I mean, if you write this metric, domain wall metric in this form, something like this, plus I think dr square. Is that the right metric? Okay, yeah, I think something like this. So then they define a c function like this. A prime to the power d minus 1. And then they prove that dc dr is actually greater than, okay, so dr of cr is actually less than equal to 0, I think. And that, because this turns out to be proportional to this null energy, I mean this combination. Okay, but here the thing is that here, so this quantity is not 1 over a prime to the power d minus 1. The one reason easy thing to show see is this way, that if you write down the c function, you will see that this c function is not local in the scale. In the sense that there is an integral which starts at from the ultraviolet, and the thing is that this is the type of c function that one gets if you use the sum rule in field theory. For example, in 2 dimension there is this sum rule that this is proportional to this integral of some b to x square. Now, you can actually define a sum rule. You can define a c function using this sum rule of this form, which is c mu, which is c uv minus cr. Let me call it r. So this is all rotationally invariant. So I can just take this r. So this is 0 to r. This is just like d to x. R squared. So this c function, if you look at this c at r, so that is given by an integral from 0 to r. I mean this form actually. So this r equal to 0 is the ultraviolet fixed point, and then you have the, okay, you go to r equal to r. Okay, so you call it r prime. Okay, so this is actually the integral is done on a circular or a disk of radius r. So it is actually that type of c function, whereas this c function is local in the energy scale. So this is not a type of c function which one would get from this.
Shamik, I'm going to ask you again. I'm sorry because it's confusing me a lot. We can use Raychaudhuri. Suppose I applied Raychaudhuri's equation to this situation. I would conclude that theta dot was less than equal to 0. This is correct?
d theta dt, right.
Okay? But now I'm getting confused about two things because you told me that at very early times theta dot is 0.
Theta dot is 0 because it's
Stationary. Yes. At very late times theta dot is 0.
Yeah. But it is not, but you can have functions like this, right?
Yeah. But now if I take theta,
In fact, that's what precisely the form of these things.
yeah, but theta dot at late times is theta dot. Sorry, theta at late times is theta at early times plus integral theta dot. And if integral theta dot is monotonic, how can theta be 0 at early and late times?
I mean, it is monotonic in the sense, I mean, okay.
It's not monotonic, it's
zero.
particular sign.
Yeah, it is greater than equal to 0.
Yeah, so haven't we reached a contradiction?
Less than equal to 0.
Doesn't matter, it's got one sign. So haven't we reached a contradiction? Because you're telling me that theta at early times is 0.
So what happens in the case of black holes?
Huh?
So if I have say I have a stationary black hole.
No, there theta is equal to 0.
No. Yeah. So no. But if I say
I
have a
thought
black
you
hole
continued to the past.
I mean, there must be
It would be
a
called
cosmic formation. So here, I think the point is that, okay, if you perhaps, yeah, but so that is okay. I don't immediately know how to answer, but it just follows from this calculation that it is indeed becoming stationary at both the ends actually.
Yeah.
Because the simplest way to see is that okay, I mean it's becoming a killing.
I understand and I know I'm saying something stupid.
Yeah, so that is actually yeah. I mean, yeah. So I have made my peace with that because of this. You can explicitly check that this is what is happening. Now, if you want to do it abstractly, just by using Rachel-Lee equation, I think what you will get is just a statement that the theta is greater than equal to 0 if you move in this direction.
But this is what I'm not understanding. Let me just repeat this. You see, Rachel-Lee's equation tells us that theta dot has a given sign.
Yeah, theta dot.
Therefore, theta at infinity is theta at 0 plus integral theta
Yeah,
dot.
but the thing is that but also this argument that you have theta dot less than equal to 0, right?
Right.
Okay, so that's the Rachel-Lee equation. So theta is decreasing. I mean, it can't increase. Now the point is that if you require that theta is 0 in the future,
Yeah.
okay, then theta has to be greater than 0.
That's exactly my confusion. But if something is 0 in the future and it's decreasing, then it has to have started out positive, not counter.
Yeah, so that is actually that. Yeah, but let's just but just from the calculation.
Okay, fine.
Yeah. So let's that's but that's what we get here. I mean, if you calculate this thing, dc d lambda, that's what you get. This is precisely the thing which has been explicitly checked actually.
I'm losing the picture of your C function. I mean,
this
is the area of the
so the C
length of the inner circle.
Yeah, no.
Times,
So the C function is just this density. So this is small length which you have here. Okay, so you have this future light cone.
Yeah.
Okay, and you are cutting it like this.
It's the length
cross
between two GD6.
Okay.
Between two GD6.
Yeah, so
because
it's the length between two values of eta.
So
Two null GD6.
one is like this, and the other one is like this. Something.
And this area of that strip.
Area, yeah.
Length.
So the length. So this is AdS-3. So you have this length.
Area of that strip.
In AdS-3, infinitesimal length.
Length. Yeah. So in higher dimension, it will be the area or volume.
And what's the claim? So you keep measuring this little
various
lengths.
Okay, so it's not a claim. Like
what's the statement? What's the statement?
The statement is this.
That this infinitesimal length keeps decreasing. Okay.
And this is the thing actually. So if you do this, this quantity d lambda of this is less than equal to 0, and then you can define this C function in this way, and then as I have written, one can explicitly check that this quantity is actually less than equal to 0, and the value at lambda equal to minus infinity, so that's near the UV boundary. You have the UV central charge, and C plus infinity, which is the infrared. You have the infrared central charge. So, yeah, so this is not a claim. I mean, this is a theorem.
So this quantity is changing from one end of lambda
Right,
to the other
right.
end
So,
of
so
lambda.
that's this thing actually. So dc d lambda is always less than equal.
And how are you connecting it to the general result about theta and stuff, about the expansion parameters?
Well, that, yeah. So you can state it like that because the
So you are
if
saying
you look
that
at
you
the
can
index,
use-
so this theta is something like this, right? I mean, theta is like something delta a, delta lambda 1.
In this case, it's d whatever. The distance is
d theta, yeah. So the thing is that so this dt lambda of a, so this theta is greater than equal to 0. So that means this a is actually, I mean, that's the statement of the second law. That if I look at the cross sectional area, then that keeps on growing. So that is this statement, but there is no just less than equal to 0. You can also write it greater than equal to 0.
Shamik, the question.
Yeah.
Yeah. So I was looking at your equation 19. Wait.
Yeah, right.
So what is this minus infinity and infinity? C of minus infinity is lambda.
Yeah. So this C is a function of lambda.
And what is the how do you parameterize lambda? Where is lambda infinity? Where is 0? Where is
Minus infinity of the boundary plus infinity.
Yeah. So that is actually okay. So you can probably see. So lambda, as lambda is going to minus infinity, this d bar is going to 0. So that actually just follows from the way this thing was defined, that dz bar d lambda is z bar. So z bar is some exponential lambda. So that goes to.
So I just try to understand how is the lambda parameterization of the curve.
It's
not
okay. So I had this vector field d bar.
Shamik, he wants to have minus infinity at the boundary plus infinity at the horizon.
Yeah. So that's the right.
Minus infinity at the boundary plus infinity at the horizon.
Minus infinity at the boundary and
Yeah,
plus
so that's
infinity at the horizon.
Yeah.
Right. So
And
yeah, so
and
that
it
just that just follows from this way these were chosen. That this I took these null generators to be the integral parts of this d bar. So that gives me just dz bar d lambda equal to z bar. So now as lambda goes to minus infinity, this z bar goes to 0. So that tells you that this z is also going to 0. And then as lambda goes to plus infinity, this z bar also goes to plus infinity. So that means lambda z goes to plus infinity. So that
so lambda.
yeah.
Okay. So this is the curve.
Yeah.
This is the curve t less than 0 or t greater than 0.
T.
Which curve are we
Sorry.
Are we talking about?
What is t?
Right.
Oh, right. So this is actually t greater than 0. Because okay, so here I am looking at this one, this part actually.
Sorry, I am not. Which part?
No.
The top.
Top.
What was
Top. He wants here top. You can't see here.
this part?
So the top light tone.
Yeah.
Oh,
The future light tone.
Yeah, right. So I should have drawn it. So the T runs in the upward direction, and this point P that has coordinate x mu equal to z equal to 0. So that means this light cone has T greater than 0. So that is the future light.
Okay. So it is minus infinity at the starting point at the boundary and lambda.
Exactly. So the lambda equal to minus infinity is these points close to here, and then as lambda increases, you go in this direction. Okay.
Okay, go inwards.
Yeah.
Okay, thanks.
Yeah.
So, is f of z going to 1 or that z equal to 0 and that z equal to infinity?
No. So as z goes to infinity, it is f of z goes to L square over L.
I say z equal to 0.
No. This is for large set. Now, as z goes to 0 near the UV boundary, fz actually goes to 1. Okay. That has to be the case because this metric reduces to your AdS metric near the z equal to 0 boundary. Okay, so this is not a. I must emphasize that this is not a claim. Here the expression is here in my. Okay, one can just very simple check one can do and.
I'm also confused about exactly the same thing that Shira is saying. See, theta dot is like c double dot.
Theta dot, okay, yeah.
Rational equation just says that the theta dot thing is some minus theta square plus omega square plus sigma square plus RED, RME, whatever it is. So they eventually you would have to face this equation that c double dot is less than or equal to 0. In your curve, it is not satisfied. In that curve, theta double dot is changing sign.
But that's not the point. The point is that so this is a plot of c lambda.
Correct.
Okay, now c lambda, this is not theta, right?
No, it's not, of course.
So
c dot.
This is just a.
Yes, that's correct. So the single derivative is theta.
Theta is actually it's a dot.
Agreed.
But theta dot is a double dot. That's what Dr. said.
That's right. So theta dot is a double dot, and theta dot has to be by rational equation if the number that you
Yeah. So that's all the standard.
But in your curve, I think c double dot is changing sign.
That's fine.
Why is it fine? It's violating Rajchandran's equation.
What do you mean? What do you mean it's violating Rajchandran?
No, I know we're saying something wrong, but help us clear up our confusion. Because it appears that Rajchandran's equation tells us that theta dot is monotonic, but in your curve, theta dot is not monotonic.
And theta dot is not.
If you draw theta dot,
c double dot. Do the second derivative of this one,
or do the first. It goes from 0 to 0 with the dot.
Okay, theta dot is less than. It is greater than equal to 0. So why can't it be 0 initially then?
Because see, suppose theta dot was.
Okay, so the thing is that I think once I finish the talk.
Okay.
Because the point is that so far, whatever I have done, even if Rajchandran were not there, this could.
I agree. It's just we want to clear up our confusion.
Yeah, right. Okay. So this does not really require Rajchandran equation. It's just high school algebra that one can do. Okay. So this way you get this. Okay. That's good. Okay, so that actually shows this thing, and this is a monotonically decreasing function as you go from the ultraviolet to the infrared. Okay, so if you now go to AdS d plus 1, this you can do the same construction, and then instead of eta, you have actually more coordinates like the theta, phi, all these things. But whatever you do, you can show that C of lambda is this quantity, which is L to power t minus 1 by 4 G Newton times it, and it's easy to check that it satisfies the same constraint. Like its ultraviolet value is UV central charge. But I think I'm almost.
Take your time, take your time.
Okay, yeah, so.
It's our fault.
No, it's not a fault. Okay. Yeah, so I had also the same type of question, but the thing is that, okay, this. Here, there is no contradiction. Anything, because I have not assumed anything from here, actually. Okay. Anyway, but you can actually, so in higher dimension, that is the form of the C function which you can construct, and then you can actually run the same story that you can differentiate and get everything done. Okay, and the point is that you can also apply it for the if you have okay, so this was for Einstein gravity coupled to matter fields. But now the point is that you can apply it to some arbitrary action, assuming that this thing actually holds, and then you can apply it to some simple theories. For example, this Einstein plus matter plus this. If you have a curvature coupling like this, then you don't have the null energy condition. But still, you can define an entropy function which actually still shows the increasing property, and using that functional, you can define a C function which is also valid even if the null energy condition is.
Okay, so Shamik, for this slide at least you need to clear up the previous confusion, right? Because you're saying that there's a generalized second law which holds.
Yeah, so this
by black hole thermodynamics, so at least we should be able to see how your earlier result follows from Einstein black hole thermodynamics, which is basically Ricciardo's equation.
Well,
you're appealing to some abstract yet unproven statement, right? That world entropy increases in time.
No.
Yes.
I'm not talking about the world entropy increasing. So what I'm assuming is that something exists which actually interpolates between two stationary things.
Something, a solution exists, and you want to prove that something increases along that.
No, I don't want to prove that. Okay. That is too
much
complicated.
Yes.
But the thing is that if I assume that such a thing indeed exists,
then you've got a c-theorem, I agree.
Yeah.
But it would be nice for that purpose to word your earlier proof in terms of standard black hole thermodynamics. Because the reason to believe that such a thing exists is black hole thermodynamics, right?
Yeah, but this has nothing to do with black holes.
But when I say black hole thermodynamics, I just mean thermodynamics of event
horizons. This is, this is just some simple thing which one can do. I mean, it has got nothing.
No, but the simple thing one can do, one has to assume Einstein gravity, positivity of, something like positivity of the stress test.
No. It's just a null energy function.
And Einstein equations, right?
Yeah.
Okay, but now you're generalizing beyond that.
Einstein equation is going in here, right? That this f prime of z is greater than equal to 0.
I know. So that follows from null energy condition and Einstein's equation.
Yeah.
Now, when you look at higher derivative gravity, there will be some as yet confusing condition that replaces this.
Yeah. So there. Okay.
So for that, just to say, you will not be able to get away with an algebraic proof, right? Because you don't even know what the condition is.
Well,
what you have
finally, everything is algebraic.
No. But the solution will be very, very complicated. I mean, if you have this theory 22.
No. Just so.
You don't even know what the conditions are, right? There's something that replaces positivity of the stress tensor.
No. Wait. So here the thing is that, so if such a thing exists,
yes.
If
yes.
I don't know if it does or not.
Yes.
And I don't say that it does exist or does not.
I understand.
If it does, then using some known things, what one can show is that you have, then you can actually define, you can show that if you evaluate this world entropy expression in the ultraviolet and the infrared, in the infrared AdS, that reduces to the ultraviolet central charge and the infrared central charge. Now, just to it. Now, the thing is that since at the beginning, my assumption is that there exists one function which is interpolating between the two world functionals in the ultraviolet and the infrared, or the two stationary black holes. So if that is true, then you can prove the C-theorem.
I agree with everything you said. I'm just saying the following, that the reason to believe this statement, that for every solution there is a functional that will always have a particular monotonicity.
No. So there is absolutely no reason to believe.
No, there's no theorem, but we anyway believe it because we believe the same.
But I thought, you don't believe that.
No, I believe it on physical grounds. Okay, but what I was saying was that in order to connect this transparency to everything previous,
No, but
it would be nice to have a
see the thing. No, nice to have.
Nice to have a proof of nice to clear up the relationship between your proof, which is algebraic, and Raychudhuri's equation, which is the basis of second law.
Okay, let me rephrase.
Yes,
Second law.
So this statement is just this one, right?
Correct.
Up to this point, you are fine.
I'm fine. Yes.
Okay, but that's all.
No, but you see, you can maybe after.
Yeah. So the thing is that so theorems are whole, but the thing is that since everything works out,
I'm sure it's right.
Yeah, no, I mean it has to be right because it is independent of whether Raychudhuri exists or not. The thing is that you can just show by explicit calculation that this is the case. Now, if you go to higher, so in this case, I am not saying that such a thing exists or under what condition it does. What I am saying is that if it does, then you can prove c-theorem in this way.
I totally agree. I'm just saying that we know that Einstein gravity does exist because of Raychudhuri's equation. That's why it would be nice to have to see the consistency of Raychudhuri's equation.
Yeah, so in this case, Raychudhuri equation, but this was, this is Raychudhuri, this is a statement of, this is just a statement of Raychudhuri equation is theta greater than equal to 0.
Let's talk about it.
What?
Yeah, I still get confused because...
No. Yeah, that's clear. But the thing is that I should emphasize that I am not saying that such a thing always exists. What I'm saying is that if it does, then you can prove the c-theorem in this way.
Okay.
So that's the whole thing.
Yeah.
And the thing is that, what was, I think, my point was that, we don't really know how to prove the c-theorem in if you have a unitary bulk theory with higher curvature things. Now, this seems to be a general way of addressing that thing, and so that's a hope that maybe there is a physical reason that why it should exist at least in these simpler cases of.
I think it's a very beautiful point that if you prove the second law of black hole thermodynamics for event horizons, you also prove the c-theorem. That's a very beautiful point. But
So for a black hole to exist, the function f has to do something in changes in a non-trivial way when you go from
one stationary.
So, but what does that do to your theta dot?
No, so in this case there is no theta dot as such because once you have the higher derivative term, you can write down a theta dot, but that does not really play any role. So here, Siraz knows more than me that how to how to work with these things actually. You have to postulate probably some kind of more general expressions, and there are recently some linearized things actually which can be which are related to entanglement entropy functionals, but then the thing was that why was it related to the linearized entanglement entropy function? Because the point is that this c-theorem connection actually, if I did not show that, but if you look at your ultraviolet and infrared fixed points which are very close, so that you can apply a linearized equation of motion. In that case, this c function is essentially the entanglement entropy. So that's one way of saying that why. Even in higher curvature cases, why the entanglement entropy functional plays a role. So I agree. So that confusion, I also had the same confusion Okay, so let me just okay, so let me finish very quickly. So okay, so with this one can actually now try to see if I have more general asymptotically AdS geometries. I mean, can one give an renormalization group flow interpretation to those kinds of geometries? And one candidate, natural, okay, I don't know whether it's natural, but one good candidate is a planar black hole or a black brain. So the dual field theory, so it's a thermal field theory. Okay, so let me just quickly go through this. So let's consider some black brain formed. So now there is no higher curvature term, nothing. It is just pure Einstein. So we have this matter collapsing to form a black brain, and at sufficiently late time when the black hole has formed, I apply the same trick here to see if such a function exists or not. Okay, now this is the black brain metric. We do the same thing. So we take a boundary point which is located at x mu equal to z equal to 0, and then we draw the future light cone from that point which is located at x mu equal to z equal to 0. So this is the geometry, so everything can be explicitly checked. So this is the equation of the future bulk light cone of that boundary point x equal to z equal to 0. So you can actually, okay, so this is a complicated thing, so you have all these things, but you can do it. So now I define my C function in the same way. So now I have an eta dependence. So previously what I had was that the C function did not depend on eta. That is because of the rotational or the Lorentz invariance of the geometry. But now this C function depends on eta, but that's not a problem. And the statement of the second law, well, I call it second law, but I plot it. Okay. Yeah. So the statement of the second law is the statement that del lambda at fixed eta is acting on this is less than equal to 0. So this is a monotonically decreasing function. So
but in this case, it doesn't go to constant at the horizon.
No, I mean there is no. Okay, first of all, there is no horizon is not playing any role here.
Sorry. So how
yeah. So let me. So this is. So okay. So I should not have drawn this picture. I just wanted to show that the black hole has formed. But the thing is that it starts here and decreases smoothly to at the black hole in singularity. Okay. So the horizon is not seen here.
It just goes through the horizon.
Yeah.
Smooth. Exactly. And the singularity is something funny. So it's a bit different from the earlier situation where you went from AdS to AdS.
Yeah, so this is different now. The thing is that I mean, if there is like if the theory is capped, then you can.
Then it could be like that.
So it is. I mean, that's what I was
just saying that in the earlier case we had theta equals 0 at 2 points.
Yeah. So
early and late. Here you have theta equals 0 only early.
Yeah. So that actually follows from if you can see here.
Yeah.
So here actually the theta is the point is that the C function is going to 0, but the theta is not well defined there. I mean it's doing something. It's at the singularity. But the thing is that okay. So this actually once you accept this, I mean this is not a difficult thing to find. But the only thing is that this thing you can define this C function, and this C function has this property that so this lambda equal to 0 is the boundary of the AdS. There it starts with the central charge of the 4P CFT, and eta and lambda s is the value of the parameter when that particular non-geodesic hits the singularity, and the statement of the second c-theorem is just that dd lambda of this quantity is less than equal to 0. Okay, now so this c function monotonically decreases from a to 0 at the curvature singularity. Now, okay, but okay, this is probably not just okay. This is, but the thing is that this thing actually exists in the field theory. I mean, that's the thing, that the field theory, unless you can show that these monotonicity theorems do not hold, also hold in the field theory, otherwise I mean this construction, well, it's not very clear that what you are going to do with that. So this is the C function, so this is stationary here, everything is fine, and that's because of the reason that the Lorentz invariance is actually Lorentz invariance is actually recovered here. Now this all along, this is actually a non-relativistic RG flow, so we don't expect like the stationarity properties of C function may not be true because the Lorentz invariance goes into that. So this is the black hole singularity, and these are C functions. You can just think of them as C functions in different schemes. Okay, but they all start at the same UV central charge and goes down to the 0.
So the various geodesics are hitting the singularity at different values of lambda.
Yeah. So that actually can be changed, but technically it is quite hard. I mean, yeah. So that's the thing. So one could actually have all of them like hit at the same points here by reparametrizing, by doing an affine transformation, but technically that is very difficult. Okay. So the thing is that this has a yeah.
What is eta again in AdS-5?
Oh, this eta. Okay. So this is you see this H3.
Okay.
So this H3 has metric dss square equal to d eta square. So this eta is the radial coordinate of this H3.
So you're taking some hyperbolic slices and the radial
exactly. So what we are doing is that this eta. So if you take the future light cone, and I am looking at space like slices of that light cone, and if you look at pure AdS, then that space like slice is just H3. I mean, in our choice of light, I see. And this eta is the radial coordinate of that H3. Is that fine?
Yeah, but so I'm just trying to understand what does this various eta mean? Like, how should
okay. Yeah. Just.
He's drawing on the board, so tell us if you can see it.
Yeah. So the thing is that so this eta. So you have this. Okay, let me just. Something like this you have. Okay, and now I am taking some cross section, some space like cross sections. Okay, so these cross sections, these space like cross sections have the geometry of Euclidean H3. Okay, so I am in AdS-5. So this is Euclidean H3. And the metric is just d eta square plus sine hyperbolic square eta d omega 2 square.
Maybe I can try something intuitive and tell me if that's wrong, right?
Yeah.
Okay. Look, you're shooting out these light rays into the bulk. Okay? And you've got a choice of direction in which to shoot them out. You have to shoot them out into the radial direction, but then you have to shoot them out in some field theory direction as well. So one choice is to shoot them out in time and radius. Another choice would be to shoot them out in some combination of time and space and radius. Now in a Lorentz invariant situation, they're all equal. But here, because you're breaking Lorentz invariance, these are not all equal.
Yeah.
So this is basically the eta. It's parameterized with the angle of shooting out. Angle with the rest frame of the fluid.
And essentially here the point is that the eta enters into the tape because in the domain geometry, so this Lorentz transformation was acting on H3. So that's why all coordinates are same. So there was no eta dependent. But now you have only this d omega 2 square. So this eta thing is wrong.
Yeah, it's just the velocity, the field theory velocity.
Yeah, so that's, or it's parameterizing a scheme.
Yeah,
in some sense. Yeah. In the RG sense, I think.
Okay, thanks.
Okay. Yeah. Okay, so we can do this. Now the point is that so the dual of these is actually okay. So we just have this pure black brain, and the dual of that is a Hartmann state. And so this C function, I mean that is not a C function in the standard sense because it's not a formation of the conformal field theory, but it's a state. It's a state in the conformal field theory. And so if you compute the Zamolodchikov C function, Zamolodchikov C function is state independent, and the point is that it will not know whether it's in a Hartmann state or in a Jackman state. Okay, so what this quantity is, I mean, does such a quantity really exist? It turns out that, okay, I'll not be able to prove this whole thing that this is monotonically decreasing, but I'll show that this you can define a quantity. Okay, so let's just go to this. Okay, so now quantum information theory actually gives us some hope that one can indeed define this thing. So the thing that it cannot be is, for example, it can't be the entanglement entropy of the finite temperature state. The reason is that if you go to the so as you know, if I take the entanglement entropy in the vacuum state of a field theory, and if I take my subsystem as a sphere of some radius r, in that case, if I have a non-conformal field theory, then one can define a renormalized entanglement entropy, which is a function of r, and as r goes, so this r is this spherical regions. For small r, you are near the ultraviolet, and for larger, you are near the infrared. And it is known, at least in 2 and 3 dimensions, that if you define the renormalized entanglement entropy, that actually acts as a C function. So that interpolates between the ultraviolet central charge and the infrared central charge, and it monotonically decreases if the field theory is in a vacuum state. But if the field theory is in a finite temperature state, then that cannot be true. So it is actually intuitively it is quite clear what happens in this case, that if you take R going to, so I define my renormalized entanglement entropy since it's a finite quantity, so it's a conformal field theory at finite temperature. So it's going to be a function of R times T. T is the temperature. So if you make R small, this quantity actually goes to the ultraviolet central charge of, say, the 4-dimensional field theory A. But as you take R, as you make R bigger and bigger, this quantity is non-zero, and it is dominated by the Hartmann entropy. But this does not match with the infrared behavior of the C function because our C function has to go to 0. Okay, now one thing it turns out, okay, I mean it was accidentally, I think it turned out that, okay, I think the calculation was done accidentally, but it turned out that it...
Shamik,
yeah.
Another question.
Yeah.
Sorry. So why can't it be just entanglement entropy minus thermal entropy?
No. Sorry. What is the question?
Entanglement entropy, but why can't it be the entanglement entropy above thermal entropy? Like
minus the thermal entropy, then it's probably not. I mean, then it's not necessarily greater than 0, perhaps. Yeah, I mean, and the point is that it has to go down monotonically, and it is always greater than 0. Now the point is that which thermal entropy we actually subtract. Yeah, so I'm not saying that this is the only possibility. So that is one possibility which this can be checked actually. Yeah. So if but okay, so one has to subtract the thermal entropy of the complete field theory. So that is a UV divergent thing, right? Okay, but. That's a different divergent thing. Yeah.
Yeah. But Shamik, so let us say I calculate a mutual information. You know, let's say divide the field theory into half and half.
Yeah.
I divide the station into half and calculate the mutual information.
Okay.
Between the two halves.
Yeah.
So I mean, why couldn't what you're calculating be that? Or something like that. So,
No, I'm not. So this is one of the things. Like, yeah. So it can be mutual information, but needs to be checked. That I mean, it is yeah. So yeah, I think it is known that at finite temperature these quantities are yeah. So this has to be checked. So I don't have any good answer to that. But thing is that this is one of the possibilities which you have. Okay, and but certainly, I mean, you can have more than one because the C function there's no unique C function for that. Okay, so let me just finish this in 5 minutes. Well, so okay. Now the reason for this is that this entanglement entropy is not an entanglement measured in a mixed state. Well, intuitively, also the point is that entanglement, I mean, quantities which are constructed out of von Neumann entropy, I mean, they are not the quantities which are measuring the quantum correlation in a mixed state. So, in that sense, if you have something like an entanglement measure for a mixed state, then that can actually play a similar role. So let's see. So there is something called this logarithmic entanglement negativity. So this was introduced by Vidal and Warner, and this is actually a computable entanglement measure for a mixed state. Okay. Let me see. Well, so okay, let me not to go into the details of this. You can define an entanglement negativity. Okay, so and the usefulness of entanglement negativity is that if you have a mixed state, although the von Neumann so if you have a separable mixed state, in that case the entanglement negativity is 0, but the von Neumann entropy or the entanglement entropy is generically non-zero. So that is one of the things which you need, because we see that in the infrared at a very high temperature, when the field theory has no quantum entanglement, so this entanglement negativity can actually maybe able to see that thing. Now this calculation fortunately was done recently. Quite recently, Calabrese, Cardi and Tocqueville, they have actually computed it for a 1 + 1 dimensional conformal field theory. At finite temperature, so the CFT lives on R11, so it is just a flat space-time. Okay, so one can compute the entanglement. Okay, I should not say one can compute the entanglement negativity. One can write down the entanglement negativity in this form. Where this L is so I have this infinite system, and I take a subsystem of length L, which is just an interval of length L, and the rest of the thing I have here. So this A is it's a short distance cutoff. We have beta is the inverse temperature, C is the central charge, C half, that is a constant, and this is the function which actually hides all the complexities of this thing. Well, now the good thing about it is that what they did is that they actually looked at the asymptotic behavior of this thing. So this quantity f, so that's a highly non-trivial function. It depends on the full operator content of the conformal field theory. Okay. Now let's see.
Yeah.
The last slide.
Yeah.
They calculate for 1 plus 1 CFT.
Yeah.
But then, why are you saying that the CFT lives in R1, 1, 1? If it is a thermal, then it should be a cylinder, right?
No, I mean, that's the Euclidean. Yeah, but in the
what is the length scale then? Where is the temperature beta?
The thing is that the field theory is, I mean, the field theory lives on flat space-time. So when you say that, okay, I mean, I have, okay, so that's the Euclidean way of doing the calculation.
Time is a
time. So this time is the real time where the field theory lives, and this beta is.
There is a Lorentzian.
Okay. Well. So now the thing is that let's check. I mean, if you are in the ultraviolet region, which is in this case the region where beta is much bigger than L, this E reduces to this, and in the infrared it reduces to this. And the important point is that this does not depend on the length of the subsystem. So at a high temperature, this logarithmic entanglement negativity becomes independent of the size of the subsystem, which is the principal difference from the entanglement entropy, because entanglement entropy reduces to the thermal entropy, which is a function of L. I mean, which is extensivity L. So now the trick is simple. If you define this renormalized entanglement, this renormalized logarithmic negativity in this way, then it's a UV finite quantity, and it is clear from here that if you differentiate with respect to L, what you will get is that the renormalized entanglement negativity, the ultraviolet value will be C/2 and the infrared value is 0, and this is precisely what we want. Now it is easy to reproduce the UV behavior of the C function, but it is actually the infrared behavior which is a non-trivial thing in this case. So I think so this okay. So I think maybe. Yeah, so this actually gives us a picture which is still not complete, but it's at least this is a hint that in AdS-CFT there are some quantities which are not okay. So this quantity certainly cannot be expressed in terms of correlation functions of local operators in the conformal field theory. Otherwise, it would have contradicted the fact that we know that if we look at the correlation functions of local operators in the one-sided black hole, then that does not know about the black hole interior. But this is a quantity which cannot be expressed. It's a highly non-local function or object which is constructed in the thermal field theory, and it turns out that at least principle which I think is okay. This if you have followed this development of complexity and all these things, that what they are saying is that if you take a two-sided black hole, if you look at the complexity of a quantum state. Now it's not the classical complexity of the state, but it's the quantum complexity which actually knows something about the black hole interior. So here we actually see the same thing. It's not the classical correlations that exist in this finite temperature state, which can actually know something about the black hole interior, but it's actually just a pure quantum correlation which exists in that particular state, which is sensitive to the physics behind the horizon. So that is one thing which I think follows more or less clearly. Well, I think I'll stop here. Already run out of time.
Maybe we should ask ICTS whether.
Okay. So one comment about mutual information which I have is that I mean this can be computed from the. So one thing is that whatever you compute, that has to somehow. Okay, the renormalization group flow interpretation of the black hole geometry that necessarily involves the black hole interior. Now the thing is that if you define some quantity, which can only be, which can always be computed by the physics outside the black hole horizon, then that is that does not seem to satisfy this condition. Well, that could be one thing because mutual information, I think one can compare. Okay. This Liu Takanagi geodesics. They will not enter the because this is a static situation, so no geodesic on one side. It's not going to enter the black hole horizon. So if that quantity is determined by the physics behind the horizon, then it is not determined by the physics behind the horizon, then it is unlikely that we really get a function like this. But okay, I might be wrong. It's just yeah.
The counterpart to that is that even for entanglement negativity, we do not know whether it grows inside the horizon.
No. The thing is that if you look at the finite temperature entanglement negativity, see here the thing is that the entanglement negativity is a quantity which cannot be geometrized in a simpler. Just the reason is that it's not a quantity which just it's not a universal function. It depends on the full operator content of the theory. So if something, it can actually really distinguish between the string theory and the non-string theory. So we can't argue in a standard way that this actually probes behind the black hole horizon. Now this is an indirect way of saying that in the bulk. The strategy is that in the bulk I prove that there is a standard renormalization group interpretation of the black-brane geometry, but that necessarily involves the black hole interior. Now, necessarily subject to the constraint that I want to construct a C function, I want to prove that this renormalization group flow, you cannot turn it back. So in that, in the more conventional sense. And I think so far attempts have been made, but it's not clear whether one can really construct a C function just by staying outside the black hole horizon. And this C function certainly has some of the expected behavior. For example, it shows that thermal states are effectively gapped, and so there is no degrees of freedom in the infrared, so this C function is going to 0. So that is the thing. So directly, I think it's I don't know. It's hard to define. There may not be a simple geometric way to see that entanglement negativity. Finite temperature entanglement, the logarithmic entanglement negativity really knows something about the physics behind the horizon, but this is a scenario like the thing is that if it behaves like if it's a C function, then that's an indirect argument, but I don't know how to make immediately how to make it better. So one way of actually proving this thing wrong will be to construct a C function just by staying outside the black hole horizon. which is actually indeed going to 0. So that if one can actually construct them, then that will cause some doubt on whether this negativity indeed does it. Yeah, so I think, so nothing is high in election, so
So Shamik,
Is IISc also there?
I think HR.
Yeah, maybe we could give them the chance.
Yeah, they can hear you.
HRI questions?
Yeah, any questions from HRI?
Can you hear me?
yeah.
Okay, can you go back to the higher derivative terms again? The one entropy,
So that actually I have not discussed that thing here. That is because of all this. I knew that this will raise many questions which I do not want to answer and do not know the answer to. But yeah, so this is the thing actually. Yeah, right.
Yeah, so the question is, suppose somebody gave you an entropy,
Right.
which you know satisfies second law.
Yes.
Can you write down the algorithm that you will use to construct the C function?
Yeah, so that is there. So we have actually constructed that thing in the explicitly in the paper. So the form of that entropy, so the form of that C function is this actually. So this C lambda, this is simply this Z bar over Z to the power D minus 1.
I doubt they can see this, Shamik. Please clear your board and write bigger.
Yeah. So these.
You use that yellow chalk if there is.
Yeah.
Is there some yellow chalk there?
No, there is only white.
Okay, now.
Okay, so the C function is like this in D dimension. So there are some powers of this L. So I have L to the power D minus 1 by 4 G Newton. So this is for AdS D plus 1. And then D bar over Z to the power D minus 1. And then, I have the S of sigma, S of lambda. So this is small s. Now what this small s is? This small s is, so this is for the domain wall geometry. So the small s, has the, so this small s actually comes from the expression which is okay. So if I just right. So if the stationary state, the world entropy is just given by some expressions like this. Is that correct? It's 7 C, right?
Yes.
Is that the expression? Right. So this is the expression. Okay. So your entropy. So your entropy expression is lambda. It is such that this quantity goes to this world entropy as lambda goes to plus minus infinity. So that's the statement. So you have given me a functional which is a locally defined functional on the slices, and the condition is that if I evaluate that functional on a stationary or a clean horizon, in that case it has to reproduce this. So this is that expression actually. And one can show that if you actually evaluate this thing, so this, it goes to here actually. So if you evaluate this quantity in the ultraviolet AdS and the infrared AdS, then it follows from a work of this Rob Myers and Sina that it actually gives you the central charge, the A central charge of the conformal field thing. So it actually the thing is that Siga caught me at some point, but the algebra actually works out so nicely that So that is the thing here actually. Okay, so I am assuming and I am not saying that such a function will necessarily exist, but what I prove is that if such a function exists, then you can prove the C-theorem in this way. And then it was quite ambitious, I think, to turn the argument around and say that, okay, we know that unitary theories, C-theorem, and this seems to be a good way of proving that, so why not the second law in all unitary theories? Yeah, so this is the expression which we actually have. So the only condition is that particular expression has to reduce to the standard word entropy when evaluated on the stationary cross sections. So that's
But you only put the boundary conditions at the two ends, right?
Yeah.
You want to prove it monotonic. Also.
No. So that will require an explicit expression.
Yeah. Suppose I'm wanting an explicit expression.
Yeah. So,
that explicit expression you are demanding something more, right?
No.
That is
No. So the only thing which is actually remaining is that whatever expression you give me, so it has to reduce to the standard word entropy when evaluated on a stationary field. So that's the only thing. That's a reasonable condition because because my entropy expression it has to interpolate between two stationary states. So it better match with the word entropy when so I'm assuming that whatever expression you give me, that's a local geometric expression, and that reduces to this form, this del R ABCD, this form when it's a filling horizon. So that's the only thing that you need.
But you are saying that expression, that given these conditions, that enough to prove monotonicity of the whole function that you are in?
No. So the thing is that, so what I have done is that, okay, so you are talking about the proof of the second law.
That's that, yeah.
No. Oh, that is of course a far more complicated thing actually. So what I am assuming is that if second law holds. So what I am assuming is that you have given me some expression which you have already checked that it satisfies the second law. In that case, given that, I can construct a C function.
Yeah, but actually what I have checked is different from what you need to prove, right?
No.
Are you saying that in the two cases you are checking exactly the same thing? The C function monotonicity and the entropy in this?
Yes, that's what it turns out to be. Yeah.
That's not obvious from what you have written, right? Or is it obvious?
No. Okay, so if I say for example, if I go back to this expression, so if you look at this equation 16, can you see this thing? This equation 16 is dd lambda of this ds Bekenstein-Hawking divided by d eta is less than equal to 0. So this is the statement of the second law, that this quantity is decreasing. Now that's the only thing. Okay, so now I write down this thing. So this is exactly this thing actually, this z bar over z. So now I define my, so the C function is this thing, this ds Bekenstein divided by d eta, which is 1 over 4 g Newton times L z bar by z. So that's my C function. And the statement of the second law is that this quantity is decreasing or say increasing if evaluated on different spatial slack axis. So that is this second.
So the smallness of lambda here is just a constant for you?
No.
So but then
no.
What
So
is the smallest lambda here?
So in the Einstein case, this is just 1.
Ashok, sorry, could I ask, do you have a separate, an independent notion of the C function that you want to compare what he's doing with?
No, I don't want to have a separate notion of the C function, but the point is that this statement presumably is dependent on the geometry, right? On which you are evaluating it.
Yeah.
For example, z bar over z, this notion is a particular geometry dependent notion, right? Because there is a domain wall.
Oh, I see. Okay, is that the question?
Yeah, that is the question. That you are evaluating them on different geometry. So how does positivity of one imply the other?
Yeah.
No. So the thing is that what I'm assuming here is that you have given me some.
Suppose S is the smallest in monotonic.
The question. What is the question, sir? The geometry.
He is saying, suppose smallest is in the monotonic. You know that.
No.
Then how do you know that?
Actually, smallest is not monotonic. What is monotonic is this whole thing actually.
Oh, that is very complicated. I mean, okay.
No. So this is actually essentially reduces to this. If you have a stationary horizon. Okay.
So then, what's the input? So you just smallest is constant or
no. Smallest is not a constant. So this quantity. Okay. So this is the world entropy used when it's stationary.
Yeah.
But now the thing is that Ashok has given me some expression which interpolates between the ultraviolet, say it goes from the ultraviolet or say from the infrared to the ultraviolet. Okay, so I have the world expression here.
Yeah.
Okay.
Just that.
I have the world expression here. Okay, and then here the Ashok's expression is here, which is interpolating between the infrared world entropy and the ultraviolet world entropy. And that's essentially the c-theorem if you specialize it to the tonal theorem.
Point is coming that this expression is monotonic in a black hole geometry, right? When one black hole is evolving to another black hole.
Oh, I think these that is I mean that. For example, the proof. One simple example which I know. For example, if you have an R phi square term, so in that case you get a different expression for the entropy. Now the proof of that, because the proof of the second law uses properties of the null geodesics. I mean they're quite
like Raisha
that is the thing. So like Raisha equation and all these things, which are true. Yeah, I mean that is so it's kind of the intrinsic property of the null hypersurface. In that sense, isn't that?
Then, in some sense, you have to really understand how the proof goes before you can make this claim, right?
No, I haven't made any claim actually. So the claim, yeah. So the thing is that what I'm saying is that suppose somebody has given me an expression which actually solves the second. Then I'm saying that okay. I mean, if you give me an expression like that, then I can construct a C C function from there. But the thing is that...
But it's not completely clear that the proof is obvious because you are evaluating the one in different geometries. Right? So unless you
by
go into
second law, well, by second law here actually, yeah. So, okay, so I did not want to say everything.
Yeah.
So the thing is that, yeah, so these are the things, I mean, the things that you are saying, I mean, I know about that, but it requires a very serious, involves a lot of calculation, which is not very clear. I mean, that will be like the proof of the second law. But the thing is that what I'm saying is that, I mean, if you give me an expression which satisfies the second law, at least in this particular geometry that I'm talking about, say this RG flow geometry. In that case, I can construct a C function from there, and I have never actually mentioned the term black hole. Because the thing is that the reason is that the black hole second law may not be like the second law of this for this causal horizons. I mean that may be more that may be more fundamental than the black hole second law because of its connection to the c-theorem. In a sense, I mean it holds in the full quantum theory, whereas the black hole second law does not. I mean it can't. I mean it's a coarse-grained thing.
But so, just one further point along the lines of Ashok's question. You know, in Einstein gravity, the second law, as you said, can be restated about some increasing of some quantity along a null manifold.
Yeah.
A non-singular null manifold. Now, in higher directive gravity, the concept of a null manifold becomes ambiguous.
Yeah. So in this case, the null manifold is only used at the endpoints.
I understand. But so the question of if it's some local statement along something, even what that something is not so clear.
Yeah. So
because, just because a manifold that is null in one metric,
but
will not be null in a field ray definition.
Yeah, but that field ray definition, if it changes the only thing, okay, I mean that does not violate the.
It does not violate anything. I'm just saying that if there is some local state,
you have G and G bar, you have some future light coming.
It's not even clear what that local statement should evolve along. Because it can't be a null manifold because that's ambiguous.
Okay, so I did not want to go.
I know. It's a very, in my opinion, very interesting point.
Yeah, but the thing is that, I mean, if you look at sufficiently simple geometries like these RG flow geometries, where, I mean, one can more or less make sense of things. Yeah, so in that case, it turns out that if you give me an expression which satisfies this causal horizon, this second law of causal horizon thermodynamics, and that is equivalent to constructing a C function. Now, the whole thing was that, okay, and you must have noticed that I have not used this second law. Like, for example, in the case of black brains, I have not used the fact that it is there. Like, I have checked that, well, it does indeed monotonically decrease and shows all the expected behavior. And then, okay, in the field theory, if you have this entanglement negativity, so that's like the dual of this second law, whatever you have. So, so in that sense.
Maybe I can. Ashok, could I ask you a question, please? Sir?
Yeah.
Go ahead.
Yeah, Ashok, there should be in string theory, there should be a notion of a causal horizon more generally speaking. Is that right? That
I would agree.
So maybe.
But I think right now it's not understood what it means.
Yes.
But the thing is that the existence of this, but it must exist. Because at least one could say that, okay, the non-perturbative definition of the second law for causal horizon is this.
Yeah. So just an interesting question might be that in a general string theory, just to understand what this causal horizon is. Can you separate regions that cannot communicate with each other? You know, in general relativity, there's a very well understood notion of that, right? This null surface. What replaces that concept in string theory, though? It doesn't impact very much. It impacts only in a detailed way on your thing. But something an interesting question, right? Just to understand a sharp notion of local causality in string theory, if that makes sense or not. That seems like almost like a prerequisite for getting some world entry.
Yeah, but the thing is causality. But also the point is that okay, if the field theory has to describe everything, including the black hole interior, then the field theory like which is causally, like outside is causally disconnected from the interior. But I think that.
But perhaps in string theory there's no notion of a causal horizon really, except for S matrices. You know, because everything's fluctuating so much that maybe the only thing that can satisfy causality really is an S matrix, and maybe you can never. I don't know, just throwing it out as a possibility. Maybe these local things.
Maybe we can think of it in a simpler way. Suppose somebody gives to Einstein gravity but still is kind. Okay? You take Einstein gravity, make some complicated field definition, and suppose somebody gives to that, and you didn't know that it's Einstein gravity.
Yeah.
Could you define a notion of causality, causal horizon there?
Yeah, so right, I think Einstein gravity, field definition.
But Ashok, there one could, at least in principle, because in Einstein gravity there's something special about this that in the sense that it's a causal horizon. By which I mean that if you change initial conditions on a slice in a certain region, the solution will change only in the interior of a future region outside that region, and then this will be signaled out in a field redefinition in the invariant way, just as being as the boundary of causality.
Yeah.
Would you agree with that, Ashok?
Yeah, okay. So, I mean, could we do something similar in hard derivative gravity?
Yeah, exactly.
Yeah, that's an interesting question actually. I mean, that is that's not very clear.
Actually, just since we're talking about this, is one thing that also confused me, but maybe Ashok can clear it up. And that when you're looking at causality in a classical, suppose we're just doing classical string theory for forgetting about quantum stuff. That when we're looking for a notion of causality in a classical theory, once you've integrated out some fields, even what the criterion is a bit confusing to me. Because the way you do, when you integrate out some higher fields, you're throwing away some data, which means you're determining the data of the fields that you've integrated out in terms of the fields that you're keeping. And that procedure of determining the data in general does not respect the light cone structure if we integrate out the fields using the Feynman propagator, which is what we normally do. So even the criterion that I suggested applied to an effective field theory, it's not clear to me that that's the right criterion. Is this correct, Ashok? Was I clear? Is this wrong?
No, I think what I'm saying seems to make sense.
Yeah.
Yeah, we really have to ask the question in a full string theory and not in an effective theory.
Yeah, otherwise the criterion is not that clear, right? It's a nice thing about S matrices that they can be computed accurately in the effective theory, because all you need for an S matrix is a time-ordered Green's function, and integrating out correctly produces that. So for S matrices you can work within the effective field theory, but because these local quantities, I'd be a bit nervous about working directly in the effective theory.
Can I ask a different sort of simple-minded question? So the examples that I know for AdS-3, CFT2, the boundary central charge is somehow related to the cosmological constant in the bound. So if you want to say, I want to relate something like Zamolodchikov to something like some black hole process, I would start the discussion of black hole thermodynamics after fixing Einstein's equations.
No. So
I fix lambda.
I'm not talking about black hole.
Well, okay, but if you want to say something like second law.
Okay, I mean these two discussions are not the same actually, because black hole things, like, okay, I mean that's very well understood, and this is okay.
No, my sort of question is sort of big picture. Why does playing with C, which in examples I know is related to lambda, have anything to do with the second one?
that is that's I mean if that were clear, then yeah, I mean it's not very clear. I mean there are some. Well, I mean I don't know. I mean I should say I don't know. Like the things that I mean why it is a c-theorem. That reason must be deeper. I mean that is not so simple. Well, I mean that will require like yeah. I mean I don't know. That why physically that why it always gives you well mathematically it is like at least intuitively one can see and then you can check in explicit examples that this is going to be the case but the point is that physically that the microscopic understanding of that is clear. There is a slight entanglement entropy related thing but that is kind of only motivational but that does not go through any complete detail.
So one more question for Ashok, if that's okay. Ashok, do you think that your string field theory might be useful for establishing a sharp notion of causality in classical string theory, if one exists?
Oh, in principle, yes, but we don't really know at present how to address this. I mean, analyticity may be a clearer goal to achieve. I mean, trying to analyticity of the gain function. Now, how to be able to causality again is a question one doesn't know.
I see. Thank you.
Yeah, so I think I'll just restate Ashok's. Yeah, so my answer to Ashok's question is that like I think he was asking me about this geometry dependence of this thing. So what I think I have shown is that if you can give me an expression which satisfies the second law of causal horizon thermodynamics in the RG flow geometry, then that is equivalent to giving a C function in the dual field theory. So that's the statement. So yeah. So now, if you ask that, how do you know that? Yeah. So that you have to give me an expression which will satisfy the second law in this particular geometry along the future light cones of some boundary points, and then the statement is that that entropy expression which will satisfy this particular second law, that is C function in the dual field theory. So that's the statement. I mean that can be, yeah, so that is essentially the thing I have actually proved. Yeah. And then of course, like the one of the things was that okay, that in any unitary theory, c-theorem must be true, and I found it like an easy way to prove c-theorem. There are really few gaps, but those are like more technical nature, and then it's well, then that actually can tell something about second law in the sense that it has to hold in some sense in order to be in order that the c-theorem in the boundary field theory holds. So that was it. But okay, that statement is okay. Of course, far more require much more complicated. Yeah. So unitarity and second law, I mean, there is a connection between that. I mean, that's a.
I'm sure.
I mean, yeah, I'm sure. I mean, it's true. So the thing is that there are these technical small gaps, but those can be fixed, and still I think because yeah. So that's so this unitarity and second law probably I think Siraz talked about this constraint in the low energy theories. So that actually goes in that direction. That why does second law should give an constraint on the low energy parameters of the theory, and it turns out okay, this unitarity relation. These are not the same second law, but well.
All second laws are the same.
They're all increasing.